Hey, welcome everyone to one of the final sessions of this conference, which is cryptography and privacy. So first of all, thank you everyone for showing up for this session. This just means that all of you are very enthusiastic about this line of work. So we would want to keep this session as interactive as possible. So come up with great questions, okay? In this session, we have 5 papers. All of them are broadly focusing on optimizing cryptography and various privacy-preserving algorithms. With that, the first paper that we have here is accelerating multi-scalar multiplication for efficient zero-knowledge proofs with multi-GPU systems. To present this work, we have Zhuoran Li. He's an assistant professor at Shandong University. His research interests include GPU algorithm design, zero-knowledge proof systems, and machine learning systems. So please take over.
Thanks for the introduction. Hello, everyone. My name is Ranggi, and I'm happy to give a talk about our work, accelerating multi-scalar multiplication for efficient zero-knowledge proof with multi-GPU systems. So this work is done by Shandong University and Ant Group. Firstly, I would like to briefly introduce what is zero-knowledge proof. It is a method for one party to prove to another that they have knowledge about a piece of secret information without revealing the actual underlying information. As an example, the prover can prove to the verifier that she or he knows the original image of a hash function without revealing it to the verifier. And ZigSnag is a sophisticated zero-knowledge proof system that produces clean proof of less than 1 kilobytes without interaction and can be quickly verified. So due to its powerful features, ZigSnag has been used in many scenarios, such as verifiable outsource, blockchain, and so on and so forth. Unfortunately, the proving step in ZigSnag is very time-consuming and usually takes several hours on a single core CPU. And even with GPU acceleration, it can take tens of seconds. So we need to seek opportunity from multi-GPU acceleration. So the same roadmap with AI, right? So our experimental data shows that MSM accounts for 78.22% of the total computation. So this is measured from CPU. And accelerating MSM is very essential for an efficient zero-knowledge proof system. So what is MSM? It is basically the inner product of a scalar vector and EC point vector. However, for elliptic point, we cannot do normal multiplication. We can only do addition. And thus, each multiplication is essentially a double and eight chain. And the single addition is also quite complex, takes dozens of big integer arithmetics. And that's the reason why MSM is so time-consuming. The most popular and powerful algorithm for MSM is the Pipinjin algorithm. Basically, it first divides the scala into several windows, and for each windows, it first sums the point with the same scala, and then sums the partial results corresponding to each scala, so each bucket. And of course, finally, we need to sum up the windows, but this part is very trivial. It can be seen that the Pipinjin algorithm is easy to parallel. For example, the sum of each bucket is independent, and we can assign each bucket to its right. But can we straightforwardly extend the single GPU implementation for multi-GPU? The answer is no. Here we estimate the number of EC operations for different number of GPUs, and we found that as the number of GPU increase, the optimal window size will decrease. The main reason is that with increasing parallel thread, the workload of bucket sum is reduced accordingly, but the bucket reduced step is not. So as the buckets reduce, computational pattern is much like a polynomial evaluation. So it is hard to enjoy massively parallel threads. So with the decrease of ice, the bottleneck changed. So the bucket sort, so it means to put the point to the corresponding bucket became the major bottleneck, and the number of bucket decreased, the number of point in each bucket will increase. And the most thread will access the same address at the same time, and this increase the cost of global automatic operations. Moreover, with the decrease of ice, the GPU utilization is reduced because of the number of buckets is reduced. So we need to assign more threads to each bucket to ensure GPU utilization. And also, as the number of ice reduced, the workload of bucket reduced became so small, and there's no need to accelerate with GPUs. So we deploy this part on CPUs in our design. Actually, this is the reason why multi-GPU prefers a small ice because it leads to less bucket and it makes the part that how to parallel small. Then we introduce some of our methodologies. So we first refine the Pipinjer algorithm for multi-GPU setup. For the new bottleneck, the bucket sort, we proposed a hierarchical bucket scatter algorithm to reduce the number of global automatic operations. So basically, each thread blocks performs a bucket scatter locally and then merge to global memory in unit or bucket, in unit or thread block rather than thread. But how we do local bucket scatter, the key challenge is how we determine the size of each bucket in advance. So there are two conventional strategies. The first is to divide the shared memory. The shared memory equally, but it causes many problems and is very unfriendly for parallel execution. And the second is famous two-pass algorithm, but it involves 2 times global memory access. So how we solve it? So we smartly utilize the relationship among the bucket ID and pointer ID and the thread ID. So we can temporarily store the compress the pointer ID and store it in registers. And at the same time, we determine the size of each bucket. So it can use one pass global memory access to determine the size of each bucket and also do the sort. On the other hand, we also optimize the most basic EC operations. So EC operation is very expensive. Each point addition operation require 14 modular multiplications and with big integers. So from about 200 to 700 bits. So it's a big integer arithmetic, and a single MSM computation can take millions of point aid. So in multi-GPU situation, window size is small, and it leads to another benefit because most EC operations are actually point accumulation. That means the Z coordinate and the ZZ coordinate is actually 1. So with point accumulation, so this operator only requires 11 modular multiplications. So we can make a dedicated kernel for the point accumulation operation, and then it benefits a lot for multi-GPU setup because the window size is small and most operations are point accumulation operations. Moreover, we executed on GPUs, we found that the register pressure is a problem. For GPUs, we usually keep all variables in registers if possible. So because it's RISS, the architecture. As each register splitting will cause millions of register transfer to and from device memory. So the register pressure is a serious problem. So we first optimize the execution sequence of the instructions. So the original one is just based on the math formula, but it's not good for executing on GPUs. We found a better or actually optimal execution sequence of these instructions. So it reduced the maximum register pressure from 9 to 7. And we highlight that it is not 9 registers, but 9 big integers, and each big integer is 12 to 24 registers. So it is a big improvement. And even if we reduce the big integer to 7, it is still a large requirement because each require 12 to 24 registers for the popular EC. And so we further propose explicit register splitting. So we explicitly temporarily save some registers to shared memory by insert the instructions to store register to shared memory and load them from shared memory. So for these red arrows. And finally, we also try to use the powerful tensor code to do the most basic operations, the big integer multiplication, like this figure. But it does not lead to a very big improvement. And the reason is that for tensor cores, the input is U int 8, while the output is U int 32. So if we multiply 2 uint 8, it will result a uint 16. And as we do not accumulate so many uint 16, this format will lead to many zeros in the uint 32. So for the result, so the resistor pressure is already a problem, and we put many zeros in it. So we try to solve it with a mechanism called on-the-fly compaction. After each multiplication, we try to eliminate the 0 bits by propagate the result from the lower bits to higher bits. Actually, even with our optimizations, the performance improvement is not significant. So you can refer to the paper. And I think the future work, our future work may focus on this. So how to make it more efficient, as tensor core is actually very, very powerful than the CUDA core, about 10 times the arithmetic throughput. So we really need to use this throughput. And this is the experimental result. The MSM operation is 6.39 times, and the end-to-end speed up is about 25 times. Why the end-to-end speed up? The end-to-end speed up is compared for multi-GPU compared to CPU. And why speed up is not so high is because we have many operations that has not been deployed to GPU. So it is mainly blocked by the part that has not been deployed to GPU. So then the future work should be port the whole zk snark system to GPU. And we also have more experiment, and the details are in the paper. Okay, thank you.
Any questions? Okay, so I'll get started. To implement your bucket gather scatter primitives for multi-GPU, did you have to come up with some custom collectives?
Sorry.
For your bucket gather scatter mechanisms on multi-GPUs, did you design some custom collectives to launch those from the tensor core?
No, but actually we use the relationship between the bucket ID, point ID, and thread ID. So as this figure shows, we found that the point to a thread, the point loaded by each thread has some patterns, because the first thread will load point 0 and point n plus 1. N is the number of thread. So actually we can eliminate some bits of the point ID. So we can store them in registers. And during this step, we count the number of points of each bucket. And at the end of local scatter, we already have the size of each bucket, so we can put the point stored in, we first need to recover the point ID stored in registers, and then store it to shared memory to collect the points of all thread in this thread block, and then collaboratively store them to global memory.
Okay.
Yeah.
Thank you. Any more questions from the audience? If not, let's thank our speaker again.
Yes, thank you.
So for the next talk, we have LazyDP, which is co-designing algorithm software for scalable training of differentially private recommendation models. To present this work, we have Juntaek Lim. He's currently a second-year master student at the Korean Advanced Institute of Science and Technology. He's supervised by Professor Minsoo. His research interests include privacy-preserving machine learning and hardware-software co-design for emerging workloads.
Hello, everyone. I am Juntaek Lim from KAIST. Today, I am going to talk about LazyDP, co-designing algorithm software for scalable training of differentially private recommendation models. This work was conducted with my colleagues Youngeun Kwon and Ranggi Hwang, and professors Kiwan Maeng, Edward Seo, and Minsoo. First, the research scope of this work. This research regards privacy-preserving machine learning with differential privacy, specifically for recommendation models. These days, many services deploying machine learning are deeply integrated into our lives. In response, both industry and academia are now focusing more on privacy issues and proposing several privacy-preserving machine learning techniques. Differentially private SGD, also known as DP-SGD, is a promising method for establishing privacy guarantees in deep neural networks. It's an extension of standard SGD training. Consider two adjacent datasets where only a single example differs. When we train two distinct models by using DP-SGD with these datasets, it ensures that an attacker cannot distinguish between these two models. Now, let's delve into DP-SGD, SGD by comparing it to SGD. I'll explain it by categorizing the model training into three stages: forward propagation, back propagation, and model update. First, in forward propagation, multiple examples form a single batch and are passed through a network to derive loss values. This procedure is the same for both non-private and private training. In the backpropagation of SGD, the weight gradients for each example, often referred to as per example weight gradients, are first calculated and then averaged to derive per batch weight gradients. Then in the model update of SGD, the resulting per batch weight gradients are used to update network weight. However, in the backpropagation of DP-SGD, per example weight gradients are clipped based on their L2 norms to restrict the effect of a single example. Then these clipped per example weight gradients are averaged. In the model update of DP-SGD, the clipped per batch weight gradients are added to Gaussian noises to generate the noisy gradients. Finally, these noisy gradients are used to update the network weights. So to sum up, DP-SGD has two additional operations compared to SGD: gradient clipping and noise addition. As our title says, you may wonder what happens when DP-SGD is applied to recommendation models. The recommendation model features a large embedding table capacity spanning hundreds of gigabytes. However, during forward propagation, only tens of megabyte scale embeddings are sparsely looked up. Due to this distinct feature, when combining recommendation model with DP-SGD training, different aspects emerge which we have not seen with other models. In particular, there is a big difference in the model update stage. The gradients of the embedding layer are extremely sparse because the value exists only for the embeddings accessed in the forward propagation. Therefore, in SGD training, only about 0.03% of the embedding table are partially updated with these sparse gradients. In contrast, DP-SGD training involves adding noises to the entire table, which results in embeddings being updated even if they are not accessed. Through this section, I will present the detailed workload characterization and identify the performance bottlenecks of private training for recommendation models. There have been a few prior works optimizing DP-SGD, referred to as DP-SGD-R and F, but all of them concentrate only on the backpropagation stage. This breakdown shows the training time when using different table sizes for non-optimized DP-SGD and the other two optimizations. When the tables are relatively small, you can observe a reduction in the time for backpropagation, leading to an overall improvement in training performance. However, when the tables get bigger, the time for model update dominates, leading to only negligible improvements. From now on, we will use DP-SGD-F as our baseline DP-SGD. This breakdown illustrates the latency during the model update stage of baseline DP-SGD. We have divided the model update stage into 3 phases: noise sampling, noisy gradient generation, and noisy gradient update. Simply put, noise sampling is an operation that generates noises of the same size as the entire table. And noisy gradient generation involves adding dense noises, sparse gradients, resulting in dense noisy gradients. Lastly, noisy gradient update is a process that updates the entire table with derived noisy gradients. This line graph indicates the entire model update latency. As the table size increases, the model update latency also increases proportionally. And the noise sampling and noisy gradient update occupy most of the latency. This result suggests that these 2 phases are the main performance bottlenecks. Now, I will introduce our approach, LazyDP, which efficiently generates the exact same trained model as that produced by the baseline DPSGD. In our approach, we first resolve the problem of the noisy gradient update. After that, we further reduce the time for noise sampling. Now, I will explain how we improve the noisy gradient update phase with this toy example. On the left is an embedding table which consists of 8 embeddings. If an embedding in the table is updated with gradients, then this black gradient patch will be attached on that embedding. For updates with noises, this gray noise patch will be attached. And embeddings that are updated with either gradient or noise will be colored red. We assume that 2 embeddings are accessed in the forward propagation, so 2 embeddings are updated with gradients. In the baseline DPSGD, the noises are added to all embeddings. Therefore, the entire table becomes the target of the noisy gradient update. It means that the updates of the entire hundreds of gigabyte scale table are required for every iteration. This is why the noisy gradient update phase takes a long time. In this situation, we also notice that most embeddings keep being updated only with noises because of the extremely sparse gradient. Hence, we thought that by delaying these repetitive noise additions, we can effectively reduce the target of the noisy gradient update. With this insight, we proposed our first idea, the lazy noise update. In recommendation tasks, indices of accessed embeddings are part of the training data. Therefore, the information about embeddings accessed in the next iteration can be known in advance, and we expressed it on the right side of the table. When applying the lazy noise update, only embeddings accessed in the next iteration are added with noises. With this approach, the target of the noisy gradient update is greatly reduced, from all embeddings in the table to only embeddings that are accessed in the current or next iteration. Then the remaining embeddings are lazily updated by delaying the noise additions until they are accessed. By this, we can effectively remove the repetitive noise additions while ensuring the final model is exactly equivalent to the one generated by the baseline DPSGD. With the first idea, the time for noisy gradient update is reduced. However, the optimization of the noise sampling part is still required. When applying the lazy noise update, multiple delayed noises should be sampled. The NAIM method to sample multiple noises is sequential sampling. In this case, 5 noises are iteratively sampled from an identical normal distribution, and then they are aggregated. To improve the noise sampling part, we proposed the aggregated noise sampling referred to as ANS. By utilizing the mathematical property on the right, the aggregated noise can be transformed into another random variable that follows a different normal distribution. By this, we can sample the aggregated noise at once instead of 5 sequential samplings. To summarize, when applying ANS on top of the lazy noise update, the time for noise sampling is also reduced, successfully solving all performance bottlenecks. Now, I will present the evaluation results of LazyDP. For training large-scale recommendation models, we leverage a hybrid CPU-GPU system which stores embeddings in CPU memory and the others in GPU. We use PyTorch and Opacus library to run a default model, which follows the MLPerf training configuration. This graph illustrates the training time for different training algorithms with various batch sizes. Comparing baseline DP-SGD and LazyDP without ANS, 1.72x speed up is achieved only with our first idea, the lazy noise update. When applying ANS on top of the lazy noise update, a 119x speed up is achieved, while also showing only about 2x slowdown over the non-private SGD. This result is for the effects of the table size. While the training time of baseline DP-SGD increases proportionally, our approach remains constant, verifying that LazyDP ensures scalable training across different table sizes. To conclude, our work consists of three main parts. Through the detailed characterization, we first root cause the bottlenecks of private training for recommendation models. Then we implemented a runtime software, LazyDP, that provides efficient and scalable private training with improved training algorithms. Our design achieves significant throughput improvements over the baseline method. Thank you for listening to my presentation. I would be happy to answer any questions. Thank you.
Thank you for the great talk. Any questions in our audience?
Hello, I'm Hyunwook from Postec, and thank you for the great talk. And I just wonder that if we want to delay the output of weight update, should we keep all the noises that are similar that has similar size of the embedding table?
You mean that how we delay the noise additions, then we have to maintain the same size of the table?
Yeah.
No. I have some backup slide related to that. And so then I will answer to your question to how to derive the number of delayed required noises. And so this is an example that I used to explain the lazy noise update. So actually there is an additional data structure named history table, which records the iteration number where the embedding is lastly updated with noises. So when you think about the 7th embeddings, the noises are added in the first iteration. So H table entry is 1. And because of the 7th iteration is used in the 4th iteration, this is assumption. So we have to add the delayed noises at the 3rd iteration. So when we add noises in the 3rd iteration, we can derive the required number of noises by the current iteration number minus the HT entry value. So we can get the derived number of noise additions. And as I explained the ANS part, we can use this number to convert the distributions, aggregate noises distribution. Yeah.
Okay, thank you.
Yeah.
Any more questions? Okay, how do you ensure quantization with the delayed noise sampling?
For the quantization? What?
Yeah. So if you like, how do you make sure that this is quantization aware?
Then your question is then your question is about the applying the quantization of this word, or
Yes.
quantization of the noises?
Yes. So basically, like if you in the first case, which is the baseline work,
Yes.
you would have to apply quantization on the embedding value plus noise. But now with the delayed noise, will it still remain quantization aware?
Actually, I think that even if there is quantization, we can also apply the ideas of this work, because
Okay.
Actually, I did not catch the relation between the quantization and this work. So
Okay,
yeah.
no problem.
Let's take it offline to
Yeah,
more
let's take it
discussion.
offline.
Yeah.
Yeah, thank you.
Thank you.
Any more questions in the audience?
Hello, I'm Jun. Thank you for your great talk. Very nice. I want to ask if there's a difference in the maximum memory usage compared to original version of this implementation. I mean, is there any the maximum memory usage differences compared to baseline?
Baseline, the memory usage, differences of the memory usage between the baseline and
Yes,
our work. Actually, I use the PyTorch as I said. So in the PyTorch, we have to store the weight gradients until they are actually updated. So when you consider that, the baseline DP actually has a weight gradient whose size is the same with the table, right? So when we use the baseline, then we have to allocate the memory space that is exactly equal to the model size because of the to store the weight gradients. But in our case, because we have much more smaller gradients, so our case has more smaller memory usage compared to baseline. That's my answer.
Let's thank our speaker again. For the third paper, we have BitPacker, enabling high arithmetic efficiency in fully homomorphic encryption accelerators. To present this work, we have Nikola Samardzic. I'm sorry, I butchered your last name.
You're good.
Okay, so Nikola graduated from MIT CSAIL and will work on quant and jump trading in London. His PhD research focused on accelerating cryptographic applications.
Cool. Thank you for the introduction, and thank you, Yi-Cheng, for the laptop. We had some last-minute issues. So with that, hello, everybody. My name is Nikola Samardzic, and I'll be presenting our work on BitPacker, enabling high arithmetic efficiency in fully homomorphic encryption accelerators. This work was done in collaboration with my advisor, Daniel Sanchez. So fully homomorphic encryption, or FHE, is a cryptographic technique that enables computation on encrypted data. This means we can use FHE to offload sensitive computation to the cloud without compromising data privacy. While FHE comes with large performance overheads over unencrypted computation, recent hardware accelerators have bridged a lot of this performance gap. So FHE operations require working with large integers. State-of-the-art FHE implementations represent large integers as many smaller integers called residues. The bit fit of these residues heavily varies based on the specific FHE program we want to run. So on the slide here, we see an example of a 64-bit word size FHE accelerator that is running a program that uses 240-bit integers that are represented using 6 residues of various sizes. We see that the large portion of the data path goes unused, shown in red here. Again, the bit width of residues varies drastically between programs and even within a program. So no single hardware word size works well for all programs. Prior work proposed various hardware word sizes ranging from 28 to 64 bits, and extensive effort was put into understanding which word size supports the most programs well. This problem is important because accelerator performance is bound by the power of its multipliers. So utilizing these multipliers well is paramount. This overhead implies more operations, more energy, and more data movement. BitPacker is a redesign of the state-of-the-art FHE implementation that allows residues to have almost arbitrary bit width. This allows us to size the residues to match the word size of the hardware. The slide shows that 240 bits could be packed to have a total overhead of only 16 bits. Note how we need only 4 residues with this representation instead of 6. This allows us to show that narrow accelerator bit widths are optimal. They use minimal power and can support all FHE programs well. BitPacker brings robust performance improvements across word sizes and architectures, even including CPUs. I'd now like to give a flavor of what CKKS computations look like. I'll then introduce CKKS rescaling and the residue number system. These two concepts will help us understand the inefficiency inherent in CKKS. Cool. So we'll start with the data types. We take a message M, which is composed of some relatively small plaintext values. We add some noise for security, and then encrypt it using a secret key to generate a pair of polynomials which form the FHE ciphertext we can compute on. CKKS provides an interface of 3 operations on large encrypted vectors: element-wise additions, element-wise multiplications, and cyclic vector rotations. Now, each ciphertext is encrypted with a small amount of error, also called noise, which grows during computation. Further, each ciphertext is encrypted at a specific scale, denoted S, which dictates the precision at which the data is encrypted. In CKKS, noise takes over the low-order bits of the mantissa. So here we see that out of the log S bits of the ciphertext scale, the bottom 15 to 20 bits are noise. That is, they're just wrong. But the remaining higher order bits are correct. Scales in CKKS are typically 30 to 60 bits to provide 10 to 45 correct error-free bits. So just like with regular computation, noise grows mainly due to multiplications. Specifically, multiplying 2 ciphertexts with scale S and noise delta produces a ciphertext with scale S squared and noise S times delta. This is pretty intuitive. Indeed, these scales and errors are no different from what you would have with ordinary fixed point computation. To keep this noise from compounding to oblivion, CKKS uses a procedure called rescaling. Rescaling effectively divides the values in the ciphertext by the original scale S. This reduces the scale and noise by a factor of S. FHE application developers carefully tune scales because they present a trade-off between precision and performance. Namely, large scales have better precision, but smaller scales have better performance. This means that most FHE programs use multiple scales, and changing scales can have application-dependent performance and accuracy implications regardless of the hardware we run the application on. To support both large and varying coefficient bit widths efficiently, all CKKS implementations, both on accelerators and CPUs, leverage the residue number system, or RNS. RNS uses the Chinese remainder theorem to represent large integers modulo a large modulus, capital Q, as many small integers modulo smaller moduli. These small integers are called residues, denoted R0, R1, etc., throughout the presentation. And the respective small moduli are called Q0, Q1, etc. Now, the magic of RNS is that now multiplication of 2 1600-bit numbers can be implemented as an element-wise multiplication of the pairwise residues. And addition works the same way. Because multiplier complexity scales roughly quadratically in bit width, arithmetic is significantly cheaper in RNS than operating on large integers directly. Okay, so now when we marry RNS with CKKS, the state-of-the-art FHE scheme, we get RNS CKKS, the state-of-the-art FHE implementation. So let's see how RNS CKKS rescaling works and why that leads to inefficiency. Rescaling is applied after multiplication, so let's first multiply this ciphertext with some other ciphertext that has the same scale. Here's the result. Note that the residues change, but not the moduli. The scale is S times bigger, so S squared. To return the scale back to S, we rescale. RNS CKKS always rescales by dividing all residues by one modulus, Q4 in this case. After the division, we can get rid of the last residue. This has the effect of dividing the scale by the modulus we dropped, that is Q4. This means that we need Q4 here to be roughly equal to S for the scale at the end to roughly match the scale at the beginning. Therefore, in RNS CKKS, Q4's bit width is constrained to be equal to the scale, roughly log S. And Arguing analogously, the same will be true for any other residue. Because residue bit width must match the scale, which is often very different from hardware word size, large portions of the data path go unused. This limitation of RNS-CKKS is the main reason why we see a broad range of hardware word sizes in FHE accelerators. Different word sizes work well with different scales. SHARP is prior work that attacks this problem most comprehensively. It studies the impact of different word sizes on performance across FHE applications and shows that many applications can be tuned so that they have both good performance and precision using RNS-CKKS with a 36-bit hardware word size. But this really stretches the limit of RNS-CKKS. And this tuning is application-specific and doesn't always work. Okay, moving to BitPacker. So BitPacker addresses the root of the problem. It completely removes the coupling between scales and residues in RNS-CKKS. This allows us to use residues that match the hardware word size. Because bits are better packed, we end up using less residues in BitPacker than in RNS-CKKS, improving performance. BitPacker's packing requires it to both add and shed residues during rescaling, while RNS-CKKS only sheds residues. This requires changing the implementation of some CKKS operations, including rescaling. So let's contrast BitPacker rescaling with that of RNS-CKKS. RNS-CKKS rescaling is shown on the right, and BitPacker will be on the left. We start with the ciphertext with scale S. Note that in BitPacker, the residues are nicely packed into hardware words, so you're seeing very little red in BitPacker. So for rescaling to make sense, again, we first need a multiplication, and here it is. So far, the story is equivalent to RNS-CKKS. The scale has just become S times bigger. Now we fix the scale back using rescaling. Here, more things happen than in RNS-CKKS. So we actually shed two moduli, Q2 and Q3 prime, and we add one modulus, Q2 prime. The scale gets multiplied by the new modulus and divided by the discarded ones. But at the end of the day, the goal is the same as with RNS-CKKS. We're trying to divide the scale by S. So the ratio of the discarded to the newly added moduli should be about S. By allowing for adding and shedding multiple moduli during a single rescale, BitPacker allows us to fully pack residues in hardware words. Now let's zoom into just the rescaling procedure of BitPacker. So as I mentioned, the key innovation in BitPacker is that we first add new moduli using the scale up operation. This in turn multiplies the scale by the new modulus. And then we discard all old moduli using a method called scale down, very similar to RNS-CKKS rescales. This returns the scale back to S. So again, there's two steps here: adding new moduli and residues and discarding the old. Okay, great. Now for the results. We evaluate BitPacker on Crater Lake, a state-of-the-art FHE accelerator, and we benchmark BitPacker on 4 large workloads and use RNS-CKKS as the baseline. Our benchmarks use the same scales as the papers that introduced them, and these range from 35 to 60 bits. Each benchmark uses at least 4 scales. So here we see performance and energy comparisons across all the benchmarks. BitPacker is Gmean 59% faster and consumes 59% less energy. The overhead of level management operations, that is those operations that are different between BitPacker and RNS-CKKS, are shown in red. We see that level management consumes less energy in BitPacker, even in relative terms. This shows that despite level management being more complex in BitPacker, it's applied on a smaller number of residues and existing functional units support it well. Because the maximum number of residues that the accelerator needs to support is lower for BitPacker, BitPacker helps reduce accelerator area by 19%. And finally, BitPacker outperforms RNS-CKKS by Gmean 24% on CPUs. Cool. So to conclude, we have presented BitPacker, a new implementation of RNSE KKS, the state-of-the-art FHE scheme. And aside from robust performance gains on CPUs and accelerators, BitPacker shows that narrow hardware word size accelerators can both support any application and are the most efficient because narrow multipliers consume less energy. All this without compromising on precision of FHE operations. Thank you for your attention, and I look forward to answering your questions.
Thank you for the great talk. Any questions from the audience?
So your work detects the coefficient moduli from the hardware size, right? Hardware word size. So there is another direction of research that detaches the scales from the moduli. So there is several works on this scale management work. So I think it is very orthogonal, but how you think about using both scheme how much speed up is made by using both scheme?
Are you, so when you talk about the second scheme, you mean sort of tuning the scale to an application, sort of minimizing the scale as much as possible, that sort of work?
Yes.
Yeah, so I mean, the way I see it is these are two orthogonal things and they both improve performance. You should tune scales and minimize them to have the best performance possible while having accuracy be good enough, whatever the definition of that is for you. And then once you're done with that, this paper does not address that at all. But once you do that, you apply BitPacker so that you get, however many integers you need packed as well as possible in either your accelerator or CPU. So I think these are complementary. They work together.
Okay. Thank you.
Thank you.
Any more questions from the audience? Okay. If not, let's thank our speaker. Thank you for the great.
Thank you.
For the fourth paper in this session, we have Zeno, a type-based optimization framework for zero-knowledge neural network inference. To present this work, we have Boyang Feng. Boyang is a researcher working on deep learning, compilers, and GPU acceleration. He received his PhD from the University of California, Santa Barbara.
Sorry, can you hear me? Okay. Okay. Yeah, it works. Yeah, thanks for the introduction. Hi, everyone. I'm Boye. Today, I'm going to talk about Zeno, a type-based optimization framework for zero-knowledge neural network inference. So the first question is, why ZKN? So as a user, I usually send my user data to the company. The company has a neural network. It processes data and gives me some authorization, like financial payment or open the door for some security system. Clearly, there is a privacy leakage. Instead, the user can have the ZKN. So instead of sending my data, I can generate a ZK proof and send it to the company. The company verifies this proof and gives me authorization. In this way, I can protect my privacy. So let's take a further look at how ZK works. So in ZK, there are two parties. One is a prover, one is a verifier. The prover knows everything, like the computation function, also input, output. The goal is to prove, hey, this actually, this f apply on this input, it gives some output y without revealing the input data. Also, ZK guarantees that the prover cannot falsify the proof. In last example, the user is the prover. Then on the verifier side, verifier only knows the proof. It does not know the input data. So the verifier verifies the proof, and the verifier cannot decode the input from the proof, right? So it cannot compromise the privacy. Because the verifier usually takes only a few milliseconds, In this work, we focus on the prover. So in short, ZK can be used for privacy. As we mentioned earlier, we can use ZK for data privacy. We can allow users to prove identity without leaking the data. Also, we can use ZK for model privacy. Basically, we can allow companies to prove their model accuracy without releasing the weights. But as you may imagine, ZK is slow. We need better performance for mass adoption. So why ZK is slow? Because we are essentially mapping a machine learning algorithm neural networks to some cryptography design called ZKP. These two are totally different. So for neural networks, it usually have like the floating point operations, which is 32-bit or 16-bit. After quantization, we have like int 8-bit. It also has lots of different types of operations and supports tensor commutation. On the other side, ZKP operates on finite field, which are, let's say, usually 254 bits or even larger integers. So if we naively encode every scalar into this large integers, we will waste lots of computation and storage space. Also, ZKP provides native support for only limited operations, and it's usually designed for scalar computation. Existing ZK framework provides some support, but it does not work very well for the neural network context. So essentially, ZKP has a special mathematical formula called constraints. Less number of constraints leads to lower latency. So usually the experienced cryptographer will manually write and optimize these constraints to make their program faster. However, this is very hard to write for, I guess, for most developers, especially machine learning developers with enough cryptography background. So existing ZK framework builds this pipeline from the arbitrary arithmetic function, then go to some circuit and get these constraints and generate the proof. However, these existing ZK framework are usually designed for scalar level ZK workload, so they fail to maintain the high level semantics during proof generation. Also, the lack of the semantic aware optimizations during compiling ZK and the lack of some n-centric system optimizations. That's why we have Zeno. In Zeno, our key idea is to export the privacy types to reduce the number of constraints, also export the tensor types to improve the parallelism. Let's first talk about the privacy type-driven optimizations. So in ZK, privacy usually comes with some cost in terms of the number of constraints. So let's say if we do the scalar multiplication, if we do two public feature times public weight, it's free, right? Because we don't require any privacy guarantee. At the same time, if we require only one of the feature or weight is private, it's also free. But if we require both are private, some constraints comes. Also, addition is free and the equality check is free. You see, there are lots of privacy-related settings to change the cost. Our compiler can automatically use this to reduce the cost of the ZKN. Let's think about an example. We have two vectors, W1, W2, also a feature X. We want to compute the dot product, which is very common in neural networks. We can minimize the number of constraints while satisfy the specific privacy requirements. So if both feature and weight are public, there is only 0 constraint. If one of them are private, there are 2 constraints, and if both are private, we take 6 constraints, right? So in this way, we can optimize our circuit according to the privacy requirement. Can we do better? Yes, that's why we have the privacy-aware native encoding. Again, let's say in this example, if we do 2 equality checks separately, we will have 2 constraints. However, our key observation is that in neural network, we usually have small bit, like 8 bits after quantization. But in ZK, we have large bit, like 254 bits. So we can encode multiple neural networks values into one ZK finite field to reduce the number of constraints by batching some computation together. Yeah, so in native encoding, we can basically encode this to equality check into one equality check and only takes one constraint to reduce the cost. Here we can usually batch more computation to for more saving. But if we batch too much computation, we may have a potential bit overflow. So in Zeno, it will automatically select the batch size and delta to minimize the latency while avoiding the overflow. So let's talk about the benefit of this native encoding. So for native encoding, it can achieve up to 8 times constraint saving without any encoding or decoding overhead. If we provide, if we provide privacy for only either feature or weight. Now let's talk about the tensor type-driven optimizations. So as we mentioned earlier, existing framework built some arithmetic circuit to automate the generation of sticky proofs. Let's say this example, we consider a dot product between two vectors of length 4 here. We are mapping it to these constraints. So using the existing arithmetic circuit, we usually break an arbitrary arithmetic function into scalar addition and multiply operations. Then we map each operation to the corresponding addition and multiply gates. And finally, we recursively inline into constraints, leading to n-squared computation. This cannot scale up if we have neural networks, right? Especially as the neural network gets larger and larger, the cost would be huge. So we have Zeno circuit design. Our key idea is to explore the commutative property of addition gates in zk-SNARK. So we can build the Zeno circuit to minimize the number of constraints, also reduce the number of computation costs, and make it faster. In terms of benefits, in this specific example, we can reduce the computation cost from 12 to 5. Also, the critical path length from 4 to 2. Usually, this leads to more parallel computation opportunities. Zeno circuits brings benefit to many types of major operators like dot product, fully connect layer, convolution pooling, and more. So you see for the length of critical paths, we usually reduce from n to some constant. Also, in terms of computation, we reduce from n-squared to linear. This makes the zk circuit much faster. Also, in our framework, we can use this. We can compose these important operators into, many kinds of neural networks. So finally, I want to talk about the performance. So this slide shows the overall speed up. If we have the private image and the public weights, we can achieve 8 times speed up. And if we keep both private image and private weights, we can achieve like 2 times speed up. So you see this example, this result shows that we can minimize the latency while satisfying specific privacy requirements. This one shows the performance benefit from native encoding. We can achieve like 3.6 times speed up on ResNet 50. Also, this speed up increases as the model size increases. This one shows the performance improvement on the circuit computation. We can achieve up to 150 times speed up for the circuit computation with our optimizations like Zeno circuits, some caching mechanism, and parallel computation. Okay, so finally, I want to talk about the raw latency. This was the end users cares a lot. So comparing with Arcworks, which is a very popular zk-SNARK framework widely used in many industry projects, Zeno can usually achieve large speed up. So let's say for VGG16, we can reduce the latency from 400 seconds to 48 seconds. This is a large improvement. Also, we can even run some large neural network like the ResNet 50 in Zeno. So I think this is a very important step towards practical ZKN. If we also compare with non-zk-SNARK, which means there is no privacy guarantee at all, we can still see some gap here between Zeno and the plain text N. I guess there are still lots of things we can improve. Let's say currently we only measure on CPU. If we add some GPU acceleration, it will be faster. Also, another direction is the sparsity. So we can use sparsity to reduce the number of computation, and which transfers to a smaller number of constraints and make it faster. Okay, that's all for my talk today. Happy to take any questions. Thanks.
Are there any questions from the audience? Okay, so you showed some evaluation on private images and private weights. How will these tensor optimizations work for like other attention mechanisms like LLMs?
Oh, okay, that's a very good question. So these optimizations, folks, I think this optimization can also be applied to any types of machine learning like LLM, right? As I have shown earlier, we can use the optimization for dot product, right? So essentially, LLM, it has the attention layer which translates to some attention mechanism, and we can break it down into some dot product and you apply the same optimization.
Thank you. There are no more questions. Let's thank our speaker.
Yes, thank you.
Okay, for our final talk for this session and for this conference, we have performance-aware scale analysis with reserve for homomorphic encryption. To present this work, we have Yongwoo Lee. Yongwoo received his bachelor's degree in computer science and engineering from POSTECH in South Korea in 2019. He's currently pursuing his PhD from the Department of Electrical and Computer Engineering from Yonsei University from Seoul, South Korea. His research focuses on compiler and runtime systems for homomorphic encryption.
Okay, thank you for introducing me. Hi, I'm Young Lee from Yonsei University, and I will introduce my work, performance-aware scale analysis with reserve for homomorphic encryption. Various applications run on the cloud services, but we cannot use private data like personal medical data on the cloud because of privacy issue. To use such data, we need to build a privacy-preserving application. Fully homomorphic encryption allows arbitrary computation on the encrypted data, so we can build privacy-preserving application with FHE. Recent FHE scheme called RNSCKKS supports efficient fixed-point arithmetic, so we can build privacy-preserving machine learning and deep learning service with RNSCKKS. So to use FHE, we need to interpret the normal program code to FHE code. FHE code only includes a small set of operations like addition and multiplication and vector rotation. So these operation set is limited, but it's enough to support complex operations like convolution and ReLU. For FHE code, we need to set parameters for each operation. For example, we need to set the encryption parameter for X, and we need to track the parameters for each operations, and then we need to add scale management operations like rescale. So we will focus on this step, and this step requires programmers to manage FHE parameters manually. I'll introduce about FHE ciphertext parameter. First, scale parameter means the size of unencrypted data. We have a fixed point value, and then we encode this value to the large integer, and the size of this large integer is a scale. We need to add encryption key to encrypt this encoded data. And encryption key has a property called coefficient modulus, which means the size of a ciphertext. This encryption key has a noise to secure the data. So if we add this encryption key with the encoded data, there is a noise in the encrypted value, so the decryption gives not exact result. So to prevent this noise to just pollute all data in encoded plain text, so we need to use large integer to reduce the effect of this noise. And there is a property called rescaling factor, which means the unit ciphertext size. And this means the word size in the ciphertext. So if we have a 60-bit coefficient modulus and 30-bit rescaling factor, we need two words to represent this encryption. So I will introduce about scale management, why we need to manage scale and how to optimize the program. First, there are several operations that affect the scale of ciphertext. For example, multiplication increases the data size because if we have two 10 bits data and multiply it, the result will be 20 bits, so multiplication increases the scale. And there is a requirement about data size and ciphertext size. That is, the data size should be smaller than the ciphertext size, because if data size is larger than ciphertext size, this ciphertext will be overflow, and then we cannot get a correct result from decryption. And the ciphertext is very important because it affects the latency. If we have small ciphertext size, we only need one word for this ciphertext. But if we have large ciphertext size, we need two words for this ciphertext. So the multiplication on this ciphertext is latency is vary from the number of words. So we need a performance or scale management because scale is increased during the computation and data size affects ciphertext size, and this leads to the latency of each operations. So I will explain about this scale management with concrete example. First, we have a data encoded with initial scale of 10 bit, and we encrypt this plain text with coefficient modulo 60 bit. Now we just squaring this x, and it gives 20-bit ciphertext because multiplication between 10 bits gives a 20-bit data. And once again, we squaring the y and we get the 40-bit scale, and multiplying y and z gives the 60-bit data size. So in this example, we use a uniform coefficient modulus of 60-bit, and it has two words. So all of this multiplication shows long latency, and it's not efficient enough. So what you want to do is reduce the coefficient modulus and reduce the latency of each multiplication. So we add rescale operation that reduces the coefficient modulus and also reduces the scale. And by doing so, we now only need one word for this ciphertext. And then to multiply this one word ciphertext with y, we also need a one word representation of y. So we drop the most significant bits of this ciphertext and get one word ciphertext. And then we can multiply these two ciphertexts. And because we reduce the ciphertext on this multiplication, the latency is reduced. So what you want to do is finding this position of rescale automatically, and there Eva, represented in PLDI, proposed a rule-based approach for this, and they insert rescale if scale is larger than a certain threshold. In this example, we can set the threshold as 40-bit, and then Eva automatically inserts the rescale, and they have a threshold to maintain the minimum scale to protect the data after rescaling, because there is noise in ciphertext, so we need to maintain the scale to reduce the effect of noise. And there is another method presented in CGO called exploration-based approach. They generate multiple optimization plans, and they apply the optimization plan and test the plan and select the better plan. And they find the best plan by iterating these two steps. First, they select to add rescale on the Z, which is same position as the previous example, and they generate the same code and show the same execution time. But they now generate another plan that inserts the rescale in the earlier position, namely Y. And if we add rescale to Y, we reduce the quotient modulus earlier, so we can make one more multiplication to perform on the one-word ciphertext. So the latency of program is reduced. And this shows the better performance. But to find this efficient optimization plan, we need to test multiple optimization plans, and it should be larger than 1,000 or 10,000 of plans. So they show a very large scale management time, but shows better latency. But if we apply a rule-based scheme, they show shorter scale management time, but shows long program latency. So there is a trade-off between program latency and scale management time. So our goal is to achieve the fast program latency with minimal scale management time. To do so, we observed about how the scale management operation reduced the latency. Basically, earlier rescale reduced the latency because they removed the words from the quotient modulus, and exactly they removed the noise and empty space. Noise means that we cannot get useful information from this region, so we can remove this freely, but removing empty space can be very problematic because empty region is reserved for the succeeding operations to increase the scale. So the empty space should be larger than the scale used by the succeeding operations, so we cannot remove all of this empty space. But there is always exists redundancy, so we need to make main use region, minimize the waste of main use region to reduce the size of quotient modulus. So we propose the reserve concept, which means the main use region in the ciphertext and used by the succeeding operations. To remove the waste of this reserve, we set the reserve of the last ciphertext is 0 because it does not have succeeding operations, so we do not need to reserve this quotient modulus. So our idea is set the reserve of the last ciphertext is 0 and calculate the reserve from backward. And then we can find the quotient modulus and scales from this reserve analysis. So please find more details in our paper about this scheme. And I'll show our result. And we used the same benchmarks from EVA and Hecate that uses 2 image processing benchmark and 3 regressions and 3 neural networks. And we show the 42% speed up over EVA, and we show 5% overhead over Hecate, which is similar to the Hecate, but we shows a little bit overhead because Hecate finds the best plan among the several plans, so they can find better plans. But they need to explore the more than 1,000 or 10,000 plans, so they use much more scale management time, so we can improve the 15,000 times faster scale management time. So we achieved the same scale management time with the simple rule-based scheme, and we achieved the same speed up with exploration-based scheme. So we also implement our compiler and open source it in this GitHub. So, and thank you for listening and ask me any questions.
Any questions? So in the reserve analysis that you show the mechanism to do the reserve analysis, is it guaranteed that you always get the most optimal solution, or is it more like a local minima that you get or a local maxima that you get, but it may or may not be the globally most optimal solution?
So your question is about optimality of our solution, right?
Yes.
But we don't guarantee the optimality, but we mention about when can we achieve the optimality. So basically we find the local optimal solution. So there is a certain condition that we can find the optimal solution. So we describe it in paper. So please read my paper for more details.
Thank you. Any more questions from the audience? If not, thank you to all of our speakers, and thank you everyone for staying back and being the audience for the session. Hope you all have a safe flight or drive home.